Okay, it's 2 minutes past 12.
It's recording.
Thank you. Thank you very much, Noel.
That's okay.
Apologies,
no
everyone. We have a few gremlins on the IT side of things, but hopefully the rest of the presentation will run smoothly. The presentation today is on an introduction to valves in the water industry, and we plan to start at 12 and finish at roughly 1 o'clock. We've got a presentation by our two speakers today with a question and answers session at the end. If you can put all your questions into the Q&A tab at the top, please, and we'll run through the questions at the end. Housekeeping, yes, the event will be recorded and it will be published on our YouTube site for listening to later, and for anyone who wasn't able to attend. As a delegate, you will get a CPD certificate. Questions, as I mentioned, to be put in the chat, and we'll get to those at the very end. Slides are available for this as well, and also at the end of the webinar, you'll be emailed those automatically as well. We don't allow AI chatbots as well, so if any of those pop-ups come up, we will stop those. We don't allow those within our webinars. Thank you. Who we are and what we do. We're in the three of us here are from the Water and Wastewater Technical Authority Committee, and we've decided we try and run as many webinars as possible to try and educate as many of our members as possible, and hopefully the topic is of interest to you. We also are a part of the Process Industries Division that hosts even more webinars, and luckily this webinar has been advertised by the Process Industries Division Hub, and that's how we've hopefully been able to reach out to more people for this webinar. We try and organise lectures, visits, seminars. If you've got any ideas, please let us know, and we can try and incorporate them next time. Equality, diversity and inclusion. At IMechE, we believe engineering is for everyone. Our vision is to foster an inclusive culture where all members, employees and the wider engineering community feel valued, develop a sense of belonging and are empowered to thrive. We are committed to embedding inclusion into every aspect of our inclusion with support from the People and Cultures team, our Culture Inclusion Committee and our Culture Ambassador Network. We celebrate diversity amongst our members, employees and the wider engineering community to ensure that we meet all the needs of our global community, driving progress and innovation in engineering for the benefit of all. And on to our talk today. I will be your host and chair for today's webinar. I will collate all those questions ready for our two speakers today, where we have James, who is an IMechE from a degree from Brighton in 2011. He began his career as a graduate mechanical engineer with IMechE, following a 2-year scholarship with the Ford Delivery joint venture. In 2016, he joined Southern Water as a design engineer to working on major capital projects across both wastewater and clean water sectors. A chartered member of the IMechE since 2016, he also works towards developing a mentor scheme within the Southern Water, with specialists, subject matter experts in clean water pumps, pressure equipment and lifting, offering technical guidance, design support and maintaining mechanical specification. James is also a member of the Water and Wastewater TAC. Then we have our second speaker for today, who is Sam. Sam graduated as well from the University of Brighton in 2016 with an MN Honours in mechanical engineering and joined Stantec. Initial assessments and asset maintenance strategies across over 60 water companies and wastewater sites. Hands-on experience provided a strong foundation for his transition to design, where he worked on major capital projects in both sectors. He's now part of Southern Water mechanical engineering team. Sam is a specialist for screens and screenings handling and HVAC equipment. Sam is a chartered member of the IMechE and also a member of the Water and Wastewater TAC. He's also served on Portsmouth and Isle of Wight committees, promoting engagement through technical lectures and networking events. He remains committed to raising awareness in the water industry and supporting fellow engineers. And thirdly, we have Chloe Sadden, who has joined us as a panel member for the Q&A session at the end of the presentation. Chloe is a senior mechanical engineer working for Southern Water. She's a chartered mechanical engineer and has over 9 years experience and has been a valve specialist for the last 5 of those. Chloe is responsible for maintaining our valve specification, answering contractors' TQs and spec deviation requests. She attends WIME's workshops to provide input on updates to the latest WIME specs for valves and other equipment. Chloe also provides the mechanical technical input to the Southern Water Framework Agreements for valves, hence why Chloe's been asked to be part of our panel at the end for our Q&A session. And with that, I would like Sam to start the presentation. Thank you.
Lovely, thanks Pam. Just give me a thumbs up if you can see that.
Sorry, I went off mic. Yes, I can see that. Thank you.
Okay, brilliant. All right, I'll start the presentation.
So here's the agenda of what we plan to run through today. Firstly, we'll be talking about generic types of valves, such as isolation, regulation, air valves, and non-return valves. We will then look at the individual types of valves that are used in the water industry. We will look at valve operation, valve selection, some valve sizing, materials used in valves, testing and commissioning, and a few other bits and pieces along the way. Before we discuss individual valve types, I'm going to run through some terminology that's used for valves. First off, full bore. This is to do with the valve throat, which has the same cross-sectional area as the pipework. So that means that when the flow passes through the valve, the velocity is unchanged, but the shape can vary. This type of valve can't be pigged or cleaned. So much eccentric plug valves, for example, rather than having a circular opening, they have a rectangular shape. Clear bore. This is where the throat of the valve is the same dimension and shape as the pipework itself. That means that you can pass solids or objects through the pipework. If it fits through the pipework, then it will also fit through the valve, and it can be pigged. The obturator is just a fancy word for the part that goes into the flow. So that can be the gate, the disc, the plug, or the needle, depending on the valve. Body. The body is just the housing of the valve, the outside of it. And then drop tight. This means that if a valve is drop tight, then it provides a full seal and there's no leakage. But some valves, for instance, metal seated valves, they leak a little bit, but it's an acceptable level of leakage. I'll now briefly discuss the classification of valves that we use in the water industry. First of all, we use isolation valves, and these either allow flow to pass or prevent flow in a pipeline system. We use regulating valves, and these are used to throttle flow in a system. We use control valves, and these actively adjust to suit the system needs. So that might be pressure reducing or pressure sustaining. We use check valves to allow flow in one direction but prevent reverse flow. We use pressure relief valves, and these limit the system pressure to prevent over-pressurization of the system. We also use air valves, and these allow accumulated air to be released from the system or to allow air in and prevent negative pressure.
Hi everyone. The first type of isolating valve I'll talk to you today about is the wedge gate valve, sometimes referred to as a sluice valve. The gate is wedge-shaped in design, and this provides a tight seal when closed. The gate itself moves in a linear motion, either up or down, in a straight line perpendicular to the flow. When fully open, it offers minimal flow resistance, allowing full bore unobstructed flow. The valve can also be used bidirectionally, allowing flow in either direction. And it's operated either by manual means, by things such as hand wheels, or it can be actuated. Common applications for isolation cover everything from unscreened sewage right through to wholesome water and everything in between. These valves are extensively used in the water industry. The valve is operated by rotating a threaded stem multiple times. This slow, deliberate motion helps avoid sudden pressure changes. Operating the hand wheel turns the stem, which raises or lowers the wedge-shaped gate. Here on the left, you can see the wedge gate valve closed, and on the right, you can see it fully open. Wedge gate valves come in two main variations. You have metal seated and resilient seated. With the metal seated, the sealing surface is metal to metal contact. Materials are usually stainless steel, bronze, or similar alloys. With resilient seated, it's a flexible elastomer which is bonded to the wedge. Materials are typically rubber, EPDM, or NBR. Resilient seat achieve drop type performance, whereas the metal seat operate within an allowable leakage rate, though in practice this is usually no more than a fraction of a single droplet of water. Wedge gate valves in general are suitable for buried applications. They can be installed in any orientation. However, for metal seated, anything installed 10 degrees or more from the vertical, they typically require wedge guides. These valves are available in large size range, but typically anything above DN 1000 is likely to be the metal seated variant. Knife gate valves are very similar to wedge gate valves, the main difference being the gate itself is a thin, sharp metal plate, and that's what's used to move into the flow path. Most common application for these types of valves are to do with thick sludge, so typically 8% or higher dry solids. The valve features a rising stem, even with actuators. It's worth saying there is a non-rising stem with bonnet available, but these are typically less common. Again, drop type performance, and these valves can also be used as a cheaper alternative to wedge gate valves for large, low pressure installations. Let's put a rough guide in there of anything above DN 600, but less than 2 bar. It's worth saying as well that these valves can be used for higher pressure systems where it's smaller diameters. So, for example, cake pumping. And WIME's 8.09, the spec for valves, specifies the use of resilient seats and sealed bonnets where the valve might be installed in a chamber which is susceptible to flooding or where zero leakage is critical.
Another type of isolation valve is the diaphragm valve. These valves have a diaphragm which is flexed into the flow path and isolates the flow. They're typically used for chemical dosing lines, and they can be used in place of pinch valves or ball valves. They're drop tight, so perform a very good seal. They can be used for a number of different chemicals, and depending on the application, the diaphragm itself can be changed for the most suitable material. Another isolation valve type is the pinch valve. The pinch valve uses a flexible sleeve, which is pinched from the top and the bottom to provide a seal. They're used for isolation of chemical dosing lines, along with diaphragm valves and ball valves. You can also use them for regulation. They are multi-turn valves, and they have drop-type performance. Ball valves are also used for the isolation of chemical dosing lines, along with pinch valves and diaphragm valves, but they're also used for potable water applications and for fuel, air, biogas and heating and cooling circuits. They can either be made of metal or plastic, but the metal ones are quite expensive, beyond 50mm diameter. They consist of a metal or plastic ball which has an orifice drilled through the centre, and that orifice is either in line with the pipework or is at 90 degrees, depending on whether the valve is open or closed. And these valves also offer drop-type performance.
Butterfly valves. These are simple in design, and they also allow for quick operation. The valve is named so because the disc supposedly resembles the wings on a butterfly. The valve is operated by rotating the disc 90 degrees into the flow path. And as we can see from the list of common applications, this is another versatile valve. However, it's not to be used where rag is present in the flow, as this can wrap around the disc, preventing full closure and potentially leading to some damage. I mentioned the valve is quick to operate, and that's because it's a quarter turn operation. Gearboxes are required on larger valves to help increase torque, and that allows for proper closure. Line variants are also available. This is where a protective lining is bonded to the butterfly disc and internals of the valve body. Materials typically EPDM within the water industry. It's worth covering that this valve can also be used for flow regulation duty. It typically provides best flow control between sort of 20 and 70 degrees open. Within the water industry, we tend to only use concentric or double eccentric butterfly valves. So these are a really useful set of top view drawings to help demonstrate the differences. So with concentric, this is where the shaft is positioned in both the body and pipe center lines. So that's your body center line. This is your pipe center line. With the double eccentric or double offset, this is where the shaft is offset from the body center line and the pipe center line. Double eccentric valves are usually used for larger installations and also where a higher pressure performance is required.
Okay, now on to regulating valves. Here we have an eccentric plug valve, which is by far the most commonly used regulating valve in the water industry. It can be used on clean water, wastewater, and even sludge applications. From the outside, it looks sort of like a ball valve, but inside, instead of using a ball, it uses a curved disc. And the profile of this disc as it opens and closes into the flow path means that the relationship between valve position and flow, or valve position and head loss, is quite linear across the operating range. It's a quarter turn valve, and it can be used with a gearbox for high torque or high pressure applications, or it can also be used with an actuator in a control system. So if you've got a particular flow or pressure set point you need to achieve, you can set the valve up to operate, to modulate to achieve those set point pressure or flow requirements. There is also a full bore version of the eccentric plug valve, meaning the disc moves entirely out of the flow path. Eccentric plug valves are also drop tight, meaning they can also be used for isolation. Another regulating valve is the piston or plunger valve. In this valve, there's a piston that moves along the flow axis, and it blocks or exposes openings which allow more or less flow to pass. They're typically used for flow regulation of potable water, particularly where there's a high differential across the valve. There are additional features that can be installed, such as the anti-cavitation device on the outlet of the valve. These valves also offer drop-tight performance. They also have linear control characteristics similar to that of the eccentric plug valve, and they are multi-turn operation. Similar to the piston or plunger valves, free discharge valves are used in end-of-line applications, particularly where there's a high dissipation of energy required. They operate by moving a sleeve closer or further away from an end plate, allowing more or less flow to pass through, hence regulation. The water discharges in a thin cylindrical curtain into the air, and it disintegrates into droplets and loses its energy. Not all of the energy is lost though, so cavitation is less likely to occur. These valves tend to be used at the bottom of dams where there's high pressure and energy dissipation is required. They're multi-turn operation and they provide drop-tight performance. needle valves are used for the regulation of flow in small diameter pipework, typically up to DN18. They consist of a tapered needle which moves up and down in the axis of flow towards a valve seat, allowing more or less flow to pass through. They're used for chemical dosing applications usually and give a very precise and linear flow characteristic.
On to control valves. The only one we'll cover today is the line pressure driven control valve. So these are self-actuated glow valves, and they use the pressure of the fluid flowing through the pipeline to regulate system parameters like flow or pressure. You don't need any external power or actuators. The valve automatically adjusts in response to changes in the upstream or downstream pressure. These are ideal for remote or energy independent installations. The valve achieves the desired operation through various pilot tube and valve arrangements. These are commonly used in wholesome water network distribution, and the control functions are shown there. So you've got pressure reducing, pressure sustaining, flow rate control, level and pump control.
Now on to check valves, or non-return valves. This is the swing disc check valve, and it consists of a metal disc which swings into the flow path, blocking reverse flow, or out of the flow path to allow flow to pass forward. It's the most commonly used valve in the water industry and can be used on clean water applications, wastewater, and also sludge. There are options to have a resilient seat or a metal seat, and the disc can be removed without having to remove the valve from the pipework. The swing disc check valve is relatively slow to operate, and this means you can get reverse flow occurring. And when there's reverse flow, the valve tends to slam shut, sending a shockwave down the pipeline, potentially leading to surge events. So to reduce the chances of this happening, springs can be installed to the valve, or levers and weights on the outside of the valve. If levers and weights are installed, then it's important to provide guarding, because it can present a hazard to people working in the area. The valve can be operated or positioned in a vertical pipework or horizontal pipework, but it's really important to note that it can only be installed with the flow direction going up. So the valve opens in the upward position. If it's orientated facing downwards, then the valve may fail to close. Also, the pivot of the valve must be on the crown or the top of the pipe. And that's the case for all swing check valves. Flow velocities. There's a typical range of suitable flow velocities for this valve, and that's between about 1 and 2.5 meters per second, but the suppliers will give you the specific requirements for their valve. But if the velocities are low, there's a risk of the valve not opening fully, and you can have a fluttering effect on the valve. And if the velocities are too high, then your head loss increases, and you can also have premature failure of the valve. The next check valve is the resilient hinge disc. This valve, the metal disc is replaced by a flexible rubber disc, and it tends to be used with sludge where you might have blockages occurring. It's better for this application because the disc doesn't have to move as far, and it also is quick to open and close, meaning you don't get the same risk of surge that you do with a conventional swing disc valve. They are more expensive to buy, and they are less available just because they're a newer design and less commonly used. Another check valve, which is less common, but we still use a lot of them in the water industry, is the recoil swing disc valve. This valve has a number of openings or doors which open when the flow passes through it, and the purpose is for these to close more quickly than having a single door that opens. and therefore you get less likelihood for reverse flow and surge occurring. They tend to be used on bigger pipework, bigger diameters, and they're big, heavy valves. They have a metal seat, so they're not drop tight. There is a little bit of leakage, and they tend to be used on high head, high velocity applications, particularly where there's a history of surge occurring. A variation of the resilient hinge disc valve is the recoil version, and in this valve, as well as the disc closing on gravity, it's assisted by a spring which closes the valve faster. But this valve does require higher velocities to keep the valve open. There are options for installing different spring stiffnesses to suit the application. The wafer check valve can be used on final effluent wastewater applications, potable water and raw water for water applications, and also on heating circuits. The design consists of two metal plates which are sprung loaded, causing the valve to close very quickly once the flow stops. The main benefit of this valve is that it's very short flange to flange dimension, means it can be installed where there isn't much space on a pipeline, or if a valve needs to be retrofitted to an existing pumping station.
A non-slam nozzle check valve is a spring-assisted axial flow check valve. So when fluid flows forward, the disc opens smoothly. As flow slows or reverses, the spring quickly pushes the disc shut. This minimises the slam that causes water hammer. The springs themselves are available in a range of stiffness, and this enables the valve dynamic closure characteristics to be matched to the system requirements. As you've probably already noted, this valve is only suitable for use with wholesome water, and that's due to the potential for blockage. These valves can be installed in any orientation. These valve types usually incur a higher head loss when compared to other check valves. The BS5154 type swing or lift valves are small bore check valves, DN50 or smaller. The swing variant is a small bronze version of a swing check valve that is used for wholesome water, final effluent, heating and cooling, and airlines. The lift variant includes a disc which moves up to allow flow to pass forward and down to prevent reverse flow. A ball check valve is a type of non-return valve that uses a free-moving ball to block or allow flow. When fluid flows forward, the pressure lifts the ball off its seat, and that allows fluid to pass. When flow reverses, the ball returns to the seat, often with the help of gravity or a spring. That seals the passage and prevents backflow. Very simple in design, the ball is the only moving part. These are commonly used in chemical dosing systems and for thick sludges. The ball itself is usually made from NBR or coated with a polyurethane. It's also available in various weights to suit different system requirements. It should also be self-cleansing as it gets rotated in the flow. The ball check valve has a slower closure speed following a reverse flow, and that results in a higher potential for surge issues. The valve is unsuitable for low pressure or low flow applications, as the ball may not lift. Let's evaluate large inline check valves. The two key factors that stand out, surge response and solids handling capacity. So speed matters when preventing backflow and water hammer. The nozzle type leads the different types of check valve with the fastest response. This is followed by the recoil resilient hinge and recoil swing disc designs. You then have the options like twin plate, resilient hinge and swing discs, while the ball check valve is the slowest to react. For applications involving solids, the ball check valve excels, offering the best capability. Resilient hinge and recoil resilient hinge types also perform well. with swing disc and recoil swing disc offering moderate capability. The non-slam nozzle and twin plate valve designs are unsuitable for media with solids. Choosing the right valve depends on the specific demands of your system.
Another check valve is the duckbill valve. This valve consists of a rubber sleeve which is curled up at the end, and when flow passes through it, it unfurls and the rubber sides separate, allowing flow to pass. As the water rises on the downstream side, creating a pressure differential, the valve then closes again. This valve is most commonly used on sludge or wastewater or even raw water applications, often seen at the coast at the end of a short sea outfall or a surface water runoff point. There are in pipeline versions of this valve, but they're not as common. We don't tend to use them in the water industry. The foot valve is a check valve which is immersed in water and is usually used to maintain the prime of a pump. So where the pump is located above the water line and water wants to travel back into the well, this valve will prevent that. Sometimes they're installed on borehole pumps, in which case they come as part of the pump, and sometimes they're separate from the pump. They tend to be used on raw water, treated water or potable water applications, and possibly final effluent which doesn't contain any rag. The foot valve, when used on a borehole pump, can be drilled, which means that a small hole is drilled in the valve and allows water to drain back during maintenance. The reason for this is because borehole pumps tend to have long rising pipes, which when full of water can be very heavy. So as the pump is lifted from the well, water can drain out and reduce the weight. Check valves are also used for anti-pollution. So where you've got a connection into a potable water network, there's a risk of contamination depending on where that feed's going to. So it might be going to a sludge plant, it might be going to a domestic supply, it might be going to a washdown hose. So depending on the risk of that use, you would select an appropriate measure of backflow prevention. So that the lowest control measure would be a single check valve, and then the next level would be 2 check valves in series with a bleed point in between, just to verify that you've got protection, that the valve is working. And then the highest level of backflow prevention using a valve is the reduced pressure zone device, and that's shown on the screen on the right here. Generally, the higher the level of protection, the greater the head loss that occurs across the valve. So that's just something to bear in mind. These reduced pressure zone devices, they tend to get quite expensive the larger they are. So for applications above 50 millimeters, we tend to use conventional check valves in series with the bleed point in between.
Under pressure, not to worry. This section covers pressure relief valves. Terrible jokes aside, pressure relief valves are critical safety devices designed to protect systems from overpressure. When pressure in a system exceeds a preset limit, the valve opens to release excess fluid or gas. This prevents damage to equipment or risk to personnel. Some general considerations include correct valve sizing and set pressure. So the valve must be correctly sized to handle the maximum expected flow during overpressure events. The set pressure should match the system's maximum allowable working pressure, and this ensures timely activation. PRV should be installed as close as possible to the pressure source, and this minimises lag. You should avoid long piping runs that can cause pressure drops or delay valve response. The discharge location should allow for safe venting, and it's worth considering isolation, maintenance and calibration. So generally, isolation valves are discouraged and that's because they introduce a risk of unintentionally blocking the only path for pressure relief. If a system experiences overpressure whilst the relief path is isolated, it can lead to catastrophic failure. That said, there are occasions where isolation is unavoidable, such as calibration or maintenance, so it's essential to install a second pressure relief valve. You can use things like a 3-port valve or similar switchover mechanisms, and that ensures at least one PRV remains online at all times, thus maintaining continuous protection. A spring-operated poppet relief valve is a direct-acting safety device. It uses a spring-loaded poppet mechanism to force a disc into a sealing seat. The relief pressure of the valve is determined by adjusting the preload on the spring. Common applications include use with wholesome water, heating and cooling circuits, dosing chemicals and air. A remote monitoring switch can be installed and integrated with SCADA or HMI systems to trigger a telemetry alarm upon valve activation. The valve also offers rapid operation, though it is prone to sticking when not used regularly. A pinch-type pressure relief valve uses a flexible elastomeric sleeve to control and relieve excess pressure in a system. The valve remains closed under pneumatic pressure and set to the required relief pressure. These valves are suitable for use across water, sludge, wastewater, and chemical applications. Over time, air pressure can drop due to minor leaks and aging seals. Therefore, maintenance required to replenish air is critical. Switches are commonly integrated to provide remote status of valve operation and low air pressure, with visibility and alarms through SCADA or HMI systems. The pallet-type pressure relief valve uses deadweight loaded pallets to protect tanks from excessive pressure or vacuum. These are used for biogas and natural gas applications, such as digesters, gas holders, and post-digestion storage tanks. You'll commonly see these installed on digesters in a duty standby sort of cow horn configuration. And these usually use a 3-way valve to ensure uninterrupted tank protection during any sort of maintenance activities. A bursting disc is a sacrificial, non-reclosing pressure relief device, and they are designed to rupture instantly when system pressure exceeds a predetermined limit. The disc is made of a metal or composite materials, and they are precision engineered to burst at specific pressures. Bursting is employed in applications where system pressure exceeds the limitations of a spring-loaded or a pinch valve, commonly in thick sludge flow scenarios. Spares are usually required, and it's important that they're kept safe and undamaged, as it could compromise the designed relief pressure.
Valve category is air valves. Air valves are needed at high points in pipework where air can collect. The design of a piping system should minimise the use of high points and air valves, but sometimes they're unavoidable. When selecting air valves for potable water applications, it's important to consider the potential for contamination. So, for example, where surge or low pressures can occur, the air valve can actually draw in contaminants from outside, such as from flooded chambers. There's 3 types of air valves that we commonly use, and these are the single large orifice air valve, double orifice, and the triple orifice. Air valves can also be used to minimise the risk of surge. So when you've got a surge event, an air valve can be used to allow air into the system and relieve the negative pressure. Orifice air valve is a variation of the ball check valve. It's used for releasing large quantities of air from a pipeline, and so it's often used on pumping stations for commissioning and also after maintenance to refill the pipeline. If the pressure drops suddenly, the larger orifice can emit large volumes of air very quickly. The internal pipeline pressure holds the valve closed if small amounts of air are present. But when there's a lot of air in the system, the valve opens and it's released to atmosphere. The dual orifice air valve consists of a large and a small orifice. So the large allows large quantities of air to escape, such as when filling a pipeline for the first time or during commissioning or after maintenance. But it also allows smaller quantities to escape, and it does so when the pipeline's under pressure. So pumping stations can often release small bubbles of air, and they can accumulate and eventually restrict the capacity of the pipeline. So a small orifice air valve allows this to escape over time. Also, due to being a small orifice, the open and closing time and profile of the air release is slower, which reduces the chance of surge occurring. Here's a diagram of a dual orifice air valve for a wastewater application. You'll see at the bottom there's a flange connection which connects to the rising main. And above that is a large chamber which has a float in it on a spindle. As large quantities of air pass through the valve, they exit through the large orifice. But as the air escapes and the water level rises, the float at the bottom gets pushed up and it closes the large orifice. The small orifice still remains open to allow smaller pockets of air to escape. The triple orifice air valve is used when there's a high air discharge flow rate required and to minimise the risk of surge. When the large orifice closes very quickly, it can cause a surge event. So this valve aims to minimise that effect.
So let's talk about valve operation. Access for valve operation is often underestimated, especially in large-scale installations. Standard manual options such as hand wheels or T-keys can require complex or costly access structures, especially when they're positioned in hard-to-reach areas. So to improve accessibility and reduce operational challenges, it's worth considering some of the following. Extension spindles or pillars bring the operating point to a more convenient location. Chain-operated mechanisms enable remote manual operation from ground level. Alternative valve orientation or gearboxes. You can optimize the positioning for easier access. And actuation. Automate valve control to reduce the need to manually access. However, you can see from the photo, you still have to think about how you access your actuators. Let's consider when to actuate a valve. When manual operation is impractical due to high torque requirements and fitting a gearbox is not feasible. The system demands automatic or remote operation for efficiency, safety, or integration with control systems. The valve is operated so frequently that manual control becomes inefficient or unsustainable. When manual operation would take too long, typically more than 10 minutes, potentially impacting process performance. When fast valve actuation is critical for safety, emergency shutdowns, or dynamic process control. Or when manual operation would expose personnel to unsafe or restricted areas. When selecting valves for different duties, WIMES 8.09 is a great starting point. It provides clear guidance and it includes a comprehensive valve selection table in Appendix K. This table helps match valve types to specific applications. So if we walk through a practical example, let's suppose we need to choose a valve for isolating duty on unscreened sewage. Here you can see that wedge gate valves are suitable for this application due to their ability to handle solids and debris. And in contrast, butterfly valves are not recommended as they are prone to blockage and may not seal effectively in such conditions.
I'm now going to talk about valve sizing. Valves are normally sized based on the flow velocity, the throttling requirements, or the pipeline pressures. We generally keep to below 4 meters per second velocity, but often much less than that, around 2 to 2.5 meters per second. It's always important to check with the manufacturer, though, to make sure that the velocities you're proposing are suited to the valve. Smaller valves in a smaller pipeline can be used. So if you're trying to restrict or throttle the flow, sometimes it makes commercial sense to reduce the pipe diameter and therefore the valve size. Not only does this potentially give you better control, but it also reduces the size of the valve and the cost, and therefore the cost of the valve as well. It also reduces the overall length, the flange to flange distance of the valve, which can be useful sometimes. If you don't size the valve correctly, it can lead to cavitation occurring. So if the velocities are too high past the valve and you're trying to throttle with it, then it can cause cavitation. And also, if the valve is too large, then you can't get the control that you're after, because the point at which the valve it can achieve the control is usually at the almost closed position, and there's not much modulation on the control there. Valve materials also play a part in valve selection. Some materials, such as plastics, have a limited pressure rating compared to the metallic alternatives. The fluid type, though, is the main factor when selecting materials. For example, chemical applications often need special resistant materials, or abrasive fluids can cause excessive wear, and so hard materials or surface finishes should be used. Potable water applications also need special consideration to ensure that no detrimental impact occurs to the water, such as taste, odour, or harmful compounds leaching out into the water. This is also relevant to any side streams that are recycled back into the head of the works. When designing a system, the installation type needs to be considered as well. For example, valves and pipelines can be installed within a building or located outside in a coastal environment. Some valves, typically wedge gate valves, can be installed directly in the ground or within a below ground chamber. Installation guidance is available in IMechE 8.03. Before being installed, valves should be stored safely to protect them from damage or contamination. And when they are installed, the internals should be checked to make sure there's no debris or remnants of packaging. The operating requirements of a valve can affect the installation as well. Some valves that operate frequently will need higher levels of maintenance and will need to be accessible, whereas others will only be operated perhaps once a year, and so access is less important as the maintenance will be infrequent. Where valves are installed above ground, they should be supported independently from the pipework so that unnecessary load isn't placed on the pipe. Flange adapters or dismantling joints should be included to allow valves to be removed from the pipework.
While we won't go into too much detail around testing and commissioning, it's important to highlight that IMechE 8.09 is again a great starting point. For specific requirements, refer to section 7, which outlines the relevant test standards. Here is a table to summarise some key considerations when it comes to testing and commissioning valves. You've got your pre-installation checks, where you confirm valve type, size and rating. It's also worth inspecting for any damage or contamination. Installation integrity, ensure proper alignment and support. Verify actuator mounting and linkage. Functional testing, perform stroke checks, 0 to 100%. Test actuator response and manual override. Control and instrumentation, validate wiring and polarity. Confirm SCADA integration and alarms. Leak and pressure testing, conduct hydrostatic pneumatic tests, check seat and body for leaks, safety and accessibility, ensure safe operation zones, and confirm fail-safe features and maintain access.
Okay.
Thank you, James and Sam. Can I confirm that you can hear me?
Yeah.
If you want to
no,
put yourselves on screen as well. Brilliant. We'll go through the questions. There are a few questions in the chat and in the Q&A section. So if I start with the Q&A section first, and we'll try and get through. Is there a guidebook that can help understand why certain valve types won't be used in certain water applications? You've already really answered that, but you can answer it again.
Yeah, so there's that selection table at the back of WIME's 8.09. That is a sort of the best starting point, really. And if you follow that, you're not going to go too far wrong, really.
Thank you, Sam. Another question. I'm not really familiar with the term clear bore, but from my understanding of full bore valves, they're all pickable. If they're not pickable, then they would be called reduced bore. Please clarify this point from your side.
So we use full bore and clear bore where, as was stated in the presentation, pipework is round, for example, but the throat of an eccentric plug valve can be rectangular. So if your pig is round, it's not going to go through a rectangular bore, even though the cross-sectional area is the same. So although it's not having an impact from a flow velocity perspective, because you can't get fairly stiff round pig through rectangular hole. So that's why sometimes you have to specify clear bore that the throat of the valve is round, so you can get pig through it. Of course, if you're ice pigging, doesn't matter, but traditional pigging where you've got big launches and that in the pipework, yeah, that's why we say clear bore.
Thank you, Chloe. For good practice with air valves, it's mentioned a value of greater than 0.2 bar. Is this gauge or absolute?
Good question. I would have said, well, it's all relative.
There's the pressure in the pipe, isn't it?
Yeah.
Gauge.
Yeah, I'd say gauge.
Questions about WIMEs and if it's a free tool.
No, but I think it's been answered in the chat. Pump sensor offer access to WIME, so if you've not got access, you need to contact the pump center
Yeah.
and obtain a subscription.
So for those who are unfamiliar, WIME stands for Water Industry Mechanical and Electrical Specifications, and it's the WIME's group. The Pump Centre is a group made up of all of the water and wastewater companies, plus a various selection of suppliers, interested parties, just to make sure that everyone's really working the same playbook. As has been stated, if you work in the water industry, you should be a member or be able to get access to membership.
Thank you, Chloe. Is there a general guidance for head loss values for different types of valves?
Look at the manufacturer's guidance. Ones we normally spend most time looking at for head loss is important for sizing are the control valves, regulator valves like butterflies and eccentric plugs. And in the data sheet you get from the manufacturer, it will give you the K values, which is a measure of flow restriction, head loss across them, and the charts of head loss to percentage opening and flow rate. Different manufacturers, they will be slightly different just because the shape and dimensions are going to be slightly different. So there's rough guidelines in various literature around, but if you want the really truly accurate ones, speak to the manufacturers.
Thank you, Chloe. On to the questions in the chat now. We've seen some suppliers offering valves in ductile iron to BS545. The valves offered to EN1563 grades, such as GJS 400, would one offer more integrity than the other?
So BS545 is much more of a pipework spec. There are bits in there, I believe, about valves and things, and 1563 is purely it's a material standard for solar cast irons. So all the wine specs say to use grades 2, 15, 63 because that's for what material standard we wish. Just like, for example, you're using a stainless steel, we want particularly grades 204, 316 for most items. Just like valves, we use one for standards, but in 1563 because that's for the materials, not for design, manufacture, installation of pipes and associated fittings. In terms of integrity, cast irons, ductile cast irons are much of a muchness. Realistically, as long as it passes the pressure tests that the manufacturer state is going to when you're ordering the valve, when you specify the valve, you're going to say whether you want it to 16 bar rated, 25 bar rated, what have you. And if it blows up, then either something's gone horribly wrong or the manufacturer's built it wrong.
Thank you, Chloe. The line pressure driven control valves, I think it's one of your slides, Sam. Are there issues with controlling the system under cooler conditions with freezing, where freezing could occur?
Yeah. So these valves are usually installed in chambers, so there is a degree of protection from frost in that respect. But it's always worth doing your trace heating and lagging assessment. I think the valve manufacturers offer some sort of additive that can be put into those lines. And it's also worth stating that due to the small bore pipe work, they're susceptible to contamination. So any particulates that work their way into the pilot tube system, that can affect the proper operation of those control valves.
Thank you, Sam. And we'll just do one of mine because I know we started a little bit later. Can you describe any problem installations with valves where the wrong valve has been installed in the wrong area and the results?
Yeah, I'll take this one. Not so much the wrong valve, but I've got an example where we installed some new metric pipework onto an existing imperial-sized pipeline, and against an existing valve which was also imperial, 30-inch. So we had 700 diameter pipeline with a 700 valve against a 30-inch small short pattern butterfly valve. And after installation, the valve failed to open because the disc of the valve clashed with the inside of the N700 pipework. That's a design and installation error. I can also talk about RGF control valves. An example where a DN400 butterfly valve was used for controlling the outlet flow of a rapid gravity filter. The valve wasn't achieving the required flow control. And when we lifted it, it was sized incorrectly, so it needed to be about 300. And we changed it for 300 eccentric plug valve, which provided the 5% per minute rate of change requirement.
Thank you very much. With that, I would like to thank our presenters and our additional panel member for that. Chloe brought some interesting extra bits to the presentation that Sam and James very kindly put together and presented today. With that, I'd just like to draw everyone's attention to the process industry webinars and recordings. They're all available on the YouTube channel. And we've got another couple coming up, managing the recovery following a major refinery fire. That's on the 1st. And then one we're hosting with the IMechE is Climate Change Has Changed, How Can Engineers Adapt? It's another one, and that's on the 9th of October. Your CPD certificates will be sent through automatically if you've attended a certain percentage of this webinar. The recordings will be available and the slides will be sent to everybody who's registered. So even if you weren't able to attend, you should get those recordings automatically. If you don't, they will be available on the YouTube channel in due course. If you want to give us any feedback, please, on today's webinar or any future webinars that you think we ought to host, please scan the QR code or email people on this chat or the IMechE committee, and we'll try and get back to you. But thank you very much. Sorry we ran over by a minute, but due to technical issues at the start, I think we're probably under the hour. But thank you very much for your time today. I look forward to seeing you all again.
Thank you, everyone. Cheers.